law of conservation of energy, you may have heard this in your other science courses, essentially means that the total amount of energy remains constant, but it may change form. We're going to use the law of conservation of mechanical energy in solving problems if there is A, little or no friction, including air resistance, and B, no collision in which significant heat is released. Here's the procedure that we're going to use in this lesson and several after that. First, we're going to take two snapshots of the system. One when the system is in one state of affairs, and another snapshot when the system is in a different state of affairs. Secondly, we're going to calculate the various energies, namely kinetic energy, gravitational potential energy, and elastic potential energy, for each snapshot. We're going to calculate those three individually for this state of affairs, then we're going to calculate those three for that state of affairs. Then we're going to sum up those energies for this state of affairs, and we're going to sum up those energies for that state of affairs, and we're going to set those sums equal to each other. And there's going to be some quantity that we don't know that through that equality we'll be able to solve for. So in this problem we have a mass that is sliding off of a shelf at a certain initial speed, and our goal is to find the mass's speed an instant before it hits the ground. So this little piggy is going to slide off the shelf and he's going to land down here, and I want to know how fast he's moving right before he hits the ground. This table is going to help us in learning how to do this conservation of mechanical energy procedure. We need to take two snapshots of this system. So snapshot A is going to be when the pig is still on the shelf. Snapshot B will be when the pig has fallen down and he is a nanometer above the floor. We're going to calculate the various energies of the piglet in snapshot A and those various energies in snapshot B. Now, we note that one of those energies is gravitational potential energy. In order to calculate that, we must define a reference line. So, I'm going to define the floor where the pig lands as the reference line. In other words, at that elevation, h equals 0. So let's total up the various energies for the piglet in the snapshot A conformation. Does the piglet have kinetic energy when he's in snapshot A? And the answer is yes, because he has a mass and he's moving. So his kinetic energy is 1/2 times m times vi squared. Incidentally, I should mention here that we're going to do this problem twice in this lesson. Once using variables, and then a second time by just plugging the numbers in. The pig also has gravitational potential energy when he's up here in snapshot A, because he has a mass. There is an acceleration due to gravity, and he is a height h above the reference line. We don't have any springs, so that term is 0. Now the piglet is down here in the snapshot B conformation, and at that location he also again has kinetic energy, but now he has a final speed instead of an initial speed. So 1/2 times m times vf squared. When the piglet is in conformation B, he is essentially at the reference line, which means his height above it is 0. So the gravitational potential energy is 0. Again, no springs to worry about, so that term is a 0. Then the conservation of mechanical energy says that the sum of these terms must equal the sum of these. So I'm going to total those down. I'm going to total the B column down. That's easy to add up. And the law of conservation of energy says that those are equal to each other. And now we just need to simplify this, solve it for the variable we need to, and then we'll plug the numbers in. Now I'm going to note here that there's an m in each of these quantities. So I'm going to effectively divide both sides by m, which gets rid of all the m's. It turns out that the mass of the piglet makes absolutely no difference to the final answer. Now I'm going to make this look a little prettier by multiplying everything by 2 so that I don't have any fractions. And now VF is what we're looking for. We're going to take the square root of both sides, and now we'll put the numbers in. VI is 6 meters per second. We're going to square that, plus 2 times G, we're going to assume we're on Earth, times H is 1.8 meters, 8.4 meters per second. Let's do the same problem, but this time we'll just plug the numbers in. There's our mass. The height of the shelf is 1.8 meters. The pig's initial speed is 6.0 meters per second, and we want the final speed when the pig hits the ground. Let's define the top conformation as snapshot A, and when the pig is just a hair above the ground, that'll be snapshot B. Again, if we're going to calculate a gravitational potential energy, we have to define a reference line. So we're going to define that, as we did on the previous slide, as the floor. The kinetic energy of the pig in snapshot A is 1/2 times his mass times his speed squared. The gravitational potential energy of the pig in snapshot A is m times g times h. No springs. Let's look at snapshot B. The pig is now down right here. Right before he hits the ground, he is moving, so he has kinetic energy equal now to 1/2 times m times a different speed squared. And that different speed is, of course, what we're looking for. When the pig is down here, his height above the reference line is 0. So m times g times h is 0 when h is 0. No springs to speak of. What we have on the left then, we want to total up this column and total up this column and set them equal to each other. Now be careful, I've seen this done before. Don't take 1/2 times 3 times 6 squared times 3 times 9.81 times 1.8. We have to multiply this product and multiply this product separately and then add those two. Right? It's the sum of these three terms. Check it out, it's 107.0. This you should be able to do in your head. 1/2 times 3 is 1.5 VF squared. The law of conservation of mechanical energy says that those two are equal to each other. We just now need to solve that for VF. Divide both sides by 1.5, take the square root of both sides, bam, 8.4 meters per second, just what we got on the previous slide. The idea of the conservation of mechanical energy can be used when a system changes from one state of affairs to another without friction and without a collision in which heat is released by the system. The procedure is simple. For one of the system's states, calculate the kinetic energy, gravitational potential, and elastic potential energy. Do the same for the new state of the system. For each case, add up the energies. Something will be unknown. Equate your two sums and solve for the unknown.